So if we have one coming in at speed v and attacking an identical object at rest, they stick together afterwards, we observe the speed is v over 2. If, on the other hand, we have two of them coming in from opposite directions, same speed, then afterwards, nothing. This is the one I just allegedly did, one coming in, two at rest, and so the speed is a third of the initial speed. And of course, if we reverse that and we had two coming in on one, we would get 2/3. This is probably not a tough question. So if I were to call the number of carts m, m times v initial would be equal to m final v final. Now, last semester you learned that this is wrong, right? I'm just going to test to see if you remember what is it supposed to say. Oh, you people, you didn't forget everything over the break. I'm impressed. Okay, so for realsies, momentum gamma m v, which is to say m v vector square root 1 minus v vector squared over c squared. And my speeds are so pedestrian here that I don't have to worry about picking up his clicker at all. But there you go. I don't have to worry about this gamma, this 1 over the square root factor. And so we will take that momentum in this course is pretty typically mv. However, on the homework assignment that's due tomorrow, the third problem will ask you to see what kind of a mistake we're making for a particular situation if we ignore special relativity. Okay. So now it is your turn. So we will, the statement here is that the number of identical carts times the velocity on the input side must be equal to the number on the output side. And you can say, well, what happens if you're not just using carts? What happens if you use carts and bulldozers or something? So how do we generalize this? How do we make sense of what m really is supposed to mean? We could do a collision between the cart and the bulldozer, measure the speed before and the speed afterwards, and figure out, based on the speeds, what the mass of the bulldozer must be. Okay? Are we good with that? All right. So now it's your turn.